Thanks a lot for the introduction. And of course, I would like to thank the organizers, Thomas, Elio, and Laura for the great invitation and for putting together once again a great meeting. And of course, I'm very happy to be here this year because last year actually failed for some, let's say, last minute COVID-19 fear, which actually turned out to be just fear, but okay. False alarm like contacts. I mean, positive contacts and wife, so not really nothing. So I would like to present you today some results about the interplay, as you see, competition or cooperation between electron-electron correlations, which are the main character of this conference, I guess, and electron-phonon interaction. So I'll start, with some, in some sense, very trivializing description of something that I think it's anyway around in the community. There is a sort of feeling, which I think it's very strong, especially in the field of superconductivity, where it's like either one or the other. There are two worlds apart, the world, of course, that I guess all of us know quite well, of conventional superconductivity, where electron-phonon coupling plays the main role. It's the glue. And usually we think there should be weak correlations. The order parameter is S wave, the critical temperature is low. Then there's what used to be the brand new word in 1986 of strongly correlated high TC superconductors, where basically all my bullet points go in the opposite direction. Almost everyone believes that the mechanism is electronic. Strong correlations play a big role, as we have seen already in this conference and many other cases. D-wave superconductivity, so the nodes of the gap are a characteristic consequence of the role of correlation, and TC is high. Then essentially, each time you have a material and you measure something where phonons seem to play a role, then people say, well, okay, if it's a superconductor, it must be BCS. If you see something like nodes, you say, well, it must be correlated. And it's like, you react almost in a Pavlovian way to these signals. But I think that once we get along and get new pieces in the puzzle, here is something like organics, and I mean many things, including fullerides, of course, the iron-based, in some sense, even magnesium diboride, or more recently, Kagome superconductors. I think that this distinction is not so clear-cut. There are things that challenge the classification, because at the end of the day, if you have phononic signatures, doesn't mean that the phonons must drive superconductivity or the other way around. And in particular, I mean, I will go through an example that I studied a lot in my life, where it's, I guess, I think right now quite clear that you have an electron-phonon superconductor where strong correlations actually play a positive role, boost superconductivity. Then I'll move along from that, discussing some more general situations which were not discussed in these old times. Here I list some things which are just really some simple examples that I don't really want to enter too much into. For example, in the cuprates, okay, almost no one believes that the phonons are the glue. Yet there are clearly effects where the lattice is playing a role. At the very least, you have charge density waves, stripes, but you also have some anomalous isotope effects, for example, on the pseudo-gap temperature, which, I mean, at least they tell you that the phonons do something. At least they react to the electron-electron physics. Then the manganites were basically the combination of double exchange and polaronic effects is the key to understand things. The fullerides that I will go through, and more, say, recently studied materials like some chromates, where we find that Jahn-Teller kind of phonons plus the Hund's coupling physics is playing a role, or the iron-based superconductors, where many of us agree that correlations are important, especially in the form of Hund's-driven correlations, but there are some phonon signatures which seem, let's say, at least very appealing in the role of superconductivity, and, for example, charge instabilities, which may be of electronic origin, but once again, they will involve the lattice at the very end. Okay, then, when you want to attach the problem of electron-electron plus electron-phonon, well, okay, but is this changing? It's not plugged in. Yeah, of course. Sure. We didn't plug in. So when you want to attack this problem, the first attempt, or at least the first model you would like to try, is what you call the Hubbard-Goldstein model. For the electron-electron part is the Hubbard model we already have seen already today, I mean, many times, and of course in advanced description. This morning, it's our paradigm from strong correlations. And somehow you would like to treat the phonon part in a similarly paradigmatic way in some sense. So you consider a local coupling of some harmonic oscillator phonon on every site with a density on each lattice site. So somehow the simplest lattice electron-phonon model. Now you immediately realize, even physically or mathematically, that this is actually a model which somehow frustrates the freedom of electron-electron and electron-phonon interaction. So in some sense, it's not that general. Because of course, what we know very well that U freezes charge fluctuations, of course. That's what increasing U does, tends to localize the electrons. Then in the system, basically what really makes you gain energy with the phonons is exactly charge fluctuations. So if U wins and freezes the density, the phonons will be ineffective, or the other way around. If the phonons win, then the Hubbard U will be ineffective. This is not just worse. It's, for example, in this phase diagram, which has been obtained by Sandro Sorella, which I'm the second person to remember today. So here you see a diagram where U measures, of course, the electron-electron interaction. Lambda measures electron-phonon coupling. You basically see that in almost all the diagram, if you are above the diagonal, U is winning and you get antiferromagnetic solutions. If you are below, lambda is winning and you get charge density waves, and you only have a tiny slice around this diagonal where something more interesting is happening, which is actually superconductivity here. Still, there is not so much space in the world of parameters to have some interesting effects. Another way to see this thing is that you can always integrate out the phonons from this model, and you obtain a retarded interaction, which has again the same form of the Hubbard U, except some frequency dependence. Before moving to situations where this fight is less, let's say, strong, less direct, let me also mention that anyway, even in the Hubbard-Goldstein model, you can get interesting stuff. This is work we did long ago with Claudio Castellani, Marco Grilli, and Giorgio Sangiovanni, where basically we have shown that when if U is large, you can basically always get some kind of effective electron-electron description for our electron-phonon problem, at least as far as the low energy properties are concerned, for example, the quasi-particle weight here. Yet, when you do it, you still find that phonons are active at high energy. They're active on the Hubbard bands. So in this is a dynamical mean field theory solution, you find that even in this case, there is already some kind of, say, distinction between the behavior at low energy, where somehow you can sort of forget about the phonons, and the high energy where you can't. But let me move to the place where the action can be more interesting, because, you know, my story basically told us that the problem of this Hubbard-Goldstein model is that you and the phonons want to do exactly opposite things. Now, if you want to have more freedom for the phonons to show up, you need to relax this thing. So one possibility would be, of course, to take a non-local electron-phonon coupling. So if your phonons do not couple with the charge, when you freeze the charge, your phonons will still have some freedom to do something. This is what I wrote here is the Phononic SSH model. And there are, of course, there are several results that show that indeed in this model, phononic signatures are stronger than for the Hubbard-Goldstein model. But I'm not going to discuss this today. Instead, I'm going in a different direction, which is the one of multi-orbital systems. We know that already at a purely electronic model, multi-orbital systems have unleashed a new world of electronic effects that go beyond the standard Hubbard paradigm, and especially the role of the Hund's coupling. So basically in this talk, I will discuss how this new, say, internal space of orbitals unleashes also the potential for a new kind of competition, cooperation between electrons and phonons. So I will start from what I already promised you, some old results that you obtained for a class of materials, where indeed we find that this interplay turns out to be surprisingly positive. It's actually a cooperation. These are the alkali-doped fullerides that I'll use sort of a North Star to orient my trip in this world of materials. Essentially, we have a class of materials where you have a lattice where C60 buckyballs fit at the lattice sites. You dope with alkali metals. The electrons of the alkali metals go into the fulleride bands, giving rise to metals that turn out to be superconductors. Until some point, basically what you were looking at were basically S-wave superconductors with all the standard phonon fingerprints you can think of. Isotope effects, jump of the specific heat, and so on, and some intermediate valued critical temperature. This is also in a classical picture, the behavior of TC as a function of the lattice spacing, which increases basically its density of state effect, like you would find in BCS. So at that time, let's say everyone was like, okay, BCS superconductors. But then a game changer appeared around 2008, which is the cesium-3 C60. Cesium is bigger than potassium and rubidium. Fullerene buckyballs are farther away. And it turns out that this material is a Mott insulator. So a close friend of our supposed pure BCS superconductors, it's actually a Mott insulator, which is basically this system here. It's antiferromagnetic Mott insulator. Then you apply some pressure and you change the volume per C60, and you will find that superconductivity comes back. You have a dome of superconductivity flanking your antiferromagnetic Mott state. And basically you can then recover and join the standard potassium and rubidium materials. So you end up building, these are some kind of different experimental phase diagrams, a unique single phase diagram where you go from something which really looks like an S-wave superconductor to a Mott insulator with the first order transition between the two. Now, what can we say about theory? So how can this happen? So if you look at what these materials are, you find out that basically you have threefold degenerate band with a bandwidth of ½ an electron volt from density functional theory. Then you measure the Hubbard U in many ways. It turns out to be around 1 electron volt, so larger than this bandwidth. So, I mean, you have to admit, no matter what you think, that electron-electron interaction is playing a role here, even in potassium and rubidium systems. And some people actually realized it early on. Then we know it's a multi-orbital system. There is also a Hund's coupling term that I write here for the fulleride system. But then there is the surprise. You take a look at the electron-phonon interaction at the active phonon modes, and you realize that they are Jahn-Teller-like modes, basically the formations of the fullerene buckyball. You integrate them out, and you get a term which is exactly like the Hund's rule, except with the opposite sign. And you look at the numbers, it turns out that the strength of the phononic part wins over the standard Coulomb-driven Hund's coupling. So at the end of the day, you can, at least as a first approximation, describe the fullerides as a system with an inverted Hund's rule. So on every site, you would like to have the minimum possible spin and minimum possible angular momentum. This comes from phonons here. Okay, so this is also a very nice model for theoretical study because all this action is local. The phonon mode is locally on a fullerene buckyball. So we can safely use dynamical mean field theory. That's what we did. And obtain a phase diagram that, to cut the story short, reproduces and in reality actually happened before the experiment was done. So you really have the S-wave superconductor and then the first order transition to the antiferromagnetic state. All fits in the experiment, and you also notice that the superconductivity you get here, when you're close to this Mott state, has a higher order parameter with respect to the one you would get for the purely phononic model without the Hubbard U. So not only if an S-wave superconductor manages to sort of survive close to a Mott transition, but it's actually benefiting from it in the sense that it's a better superconductor with a larger order parameter. Very good. Everything turns out too well, and you would like to understand why this is happening. Of course, cannot just be a miracle. So you go back to your interaction. This is what the with the plus sign is the inverted Hund's coupling that comes from the phonons. So basically, what you realize here is that the story is quite different from the one I told you at the very beginning, because now what the phonons would like to do is minimize the spin, minimize the angular momentum, and this is something that you can do also when you freeze charge fluctuations. You localize 3 electrons per site, but you can still choose them to be in a spin 3/2 or a spin 1/2. You pick spin 1/2 and you're happy, you gain energy. So our phonon mode is still active even in the Mott state when charge fluctuations are completely frozen, in sharp contrast with the Holstein model I showed you at the very beginning. In the end of the day, that's the catch. This is the reason why this phonon mode survives, and it's actually even enhanced because essentially you have the same pairing you would have for the non-interacting system as to fight with the reduced effective kinetic energy, the normalized quasi-particles that we are familiar with because the Hubbard U is large. Okay, so basically, from this sort of oldish story of the fullerides, we learned that we should look for phonons coupled with a degree of freedom which is not the charge to find something interesting in the presence of electron-electron interaction. Of course, this was just, it was basically a model calculation which did not include several aspects. So realistic modeling of the system for finite temperature, and it was treating the phonons in an anti-adiabatic way. We integrated them out and turned them into a static interaction. So that does not include phonon dynamics. So in the following, I will briefly discuss some of the steps going towards reality and also towards a more generic modeling. So here I cut very short this part. Then we did what now, we can sort of do. So we build a realistic description of these systems. This has been done by Yusuke Nomura, Ryotaro Arita, and Shiro Sakai, essentially. So we build the single particle, so the DFT part, from the DFT part, we get the bands. We obtain the CRPA method, we obtain the effective interaction, and with a similar constrained density functional perturbation theory, the electron-phonon modes. We plug all of these in the same kind of machinery, and the good news is that basically at the end of the day, we still get a similar phase diagram, and we even get some quantitative agreement with experiments, including this, the strength where you have the Mott transition here, and remarkably, the size of the critical temperatures, which is really in the right ballpark, which is quite an amazing result. So the fulleride part works. So in these specific systems where you have these very nice structures, buckyballs and so on, phonons and electrons and electron-electron interactions can really, marry each other with a very nice collective result. Now, let me go in a more generic situation. So now where I want to include the phonon dynamics and discuss things in more details using a simpler model description. So I will start from two orbitals. When you have two orbitals and you consider an octahedral environment, basically you have 3 phonon modes, which are coupled respectively with the difference of population between two orbitals, their hybridization, or the full density. These are basically, and they correspond to some specific deformations that I'm not going to discuss in details. Okay. So now what I do, I will study with dynamical mean field theory, a model where I consider these two orbitals with their Hubbard-like and Hund interaction, considering only density-density interactions, plus one of these Jahn-Teller-like modes, the one where you couple with N1 minus N2, the difference of occupation between the orbitals. Okay, you see that despite being a simple model, you already have many parameters. You would have the density, J, U, lambda. So I don't want to show you diagrams in 4 or 5 spatial dimensions. So we'll always keep the ratios of J over U and lambda over U fixed. So basically as if you were considering an experiment where you apply pressure and you change the hopping. And at least for the first part, I will stick to a half-filling configuration. Good. No, now let's start from some limits to understand something. Let's not just jump into the final results. So let me first consider Hubbard U plus Jahn-Teller phonons, but no Hund's coupling. So in these plots, the blue line is even U equals 0. So this is just Jahn-Teller phonons. So basically, if you look at this line, so Z quasi-particle weight. So this is the classical picture of a metal insulator transition. So in increasing the electron-phonon coupling, you are witnessing a metal insulator transition. What's happening there? Well, what you see is that, first of all, you see that the number of excited phonons, which is here, is growing a lot. So your insulating state is very populated by phonons, and it has a low spin. You see here the blue line again, and a large number of doubly occupied configurations on each of the orbitals. So this is not a Mott transition, clearly. We are not, I mean, the number of double occupancy is rising and so on. What we are having here is what you would call a bipolaronic metal insulator transition. So what you're doing, you're cranking up your electron-phonon interaction, your electrons couple with the lattice, they become polarons, the polarons pair together, and you end up in an insulator formed by these polarons. So this is the blue line, no doubt. And by the way, I mean, the picture are exactly like for a single band Holstein model that I studied long ago with Sergio Sciucchi. But now let's include the Hubbard U. So common wisdom would be U fights with this result, but it's exactly the other way around. You see that if I use, notice these are both plots for large U. U is twice lambda, 5 times lambda, but still you see that Z drops faster. So it means that your transition is happening for a smaller electron-phonon coupling. So U is helping it. And indeed, you look at all the observables, you find it's the same transitions. Phonons increase, double occupancy goes up. So it's really the same bipolaronic transition, which actually survives, and it's boosted by our Hubbard U. Okay, so this is a version for the metal insulator transition of this positive effect of U on a phononic property. Why is this happening? Well, you can realize easily that just like for the Holstein model, what the phonon do can be described in terms of an effective interaction, where you would like to have the largest value, possible value for N1 minus N2. This means that these two configurations, if this is 1 and this is 2, are the most favored. So if your system is in this configuration, you gain a lot of energy. Now, these are both configurations that have 2 electrons per site, and the Hubbard U is very happy about those. So this is exactly why they are cooperating, because what U does is filter configurations with 2 electrons per site, kicking out all configurations with 1, 3 electrons per site. But the 2 configurations that make the phonons happy are exactly of this kind. So they go hand in hand. There's no competition. That's actually a cooperation to filter out these configurations. And indeed, if you go there and you look at this phonon distribution function, you see that there is this bimodal description. So the phonons have a value, a typical value, which can be this positive or negative value, which is associated with these 2 local configurations. Okay, so here you see that you already have something that you could consider a surprising result, a purely bipolaronic transition, which is favored by the Hubbard U. Now, let's go in the opposite limit. Let's switch on the Hund's coupling and start with a small electron-phonon coupling. Now this, again, you see Z is going to 0, but now you look at the rest. You see that this is a Mott transition. Double occupancy is going down. Your spin is large because you have a Hund's coupling. So this is just the standard Mott transition towards a high spin state. You switch on the phonons. This is the whatever orange line here. You see that basically you still have the same transition. Slightly harder to get, but still there. You try to increase the number of phonons, but then you give up. So here, basically, the presence of J is killing the phonons, just like the presence of U was killing the phonons in my first slide, because this phonon mode couples with N1 minus N2. So if the Hund's coupling is larger than the electron-phonon coupling, you end up in this state with high spin. Now we can see what happens if we just crank up the electron-phonon coupling from one limit to the other, and we can cross. So and we can cross somehow some boundary. We should, because of course we have to go from one regime to another. And that's what we find. You see that basically when we cross, so for lambda, which is smaller than this 1.5, you see basically the result that you would get without phonons. If lambda is larger than 1.5, you get the results for the bipolaronic insulator. If you sit exactly at this 1.5, you end up in some intermediate situation where basically all the observables have an intermediate result, number value. You can, I think I have to cut short. You can, this is not magic, of course. Basically, you can understand it once again doing the integration of the phonons, assuming everything antidiabatic. You find out that your phonons will renormalize differently the interorbital and the intraorbital interactions. Then if you go and compare basically your intraorbital interaction with the smallest of the interorbital ones, you'll find you estimate a boundary, and this boundary is exactly the one I found with my DMFT calculations. So basically, you can understand everything very easily in terms of effective interactions, and you have this direct transition between a state, a bipolaronic state, where the Hubbard U helps. So you have a bipolaronic Mott insulator, because this guy can be considered either a bipolaronic state, but also a Mott insulator, because U is large and you have 2 electrons per site. And then you have this transition to the high spin Mott insulator, which happens along this line, which is, as I told you, this lambda equals 3/2 of J that you can easily estimate. So overall, you build this phase diagram where, of course, where everything is small, you obtain your metal. Then you crank up your interactions. Now you focus on lambda and J, and you end up either in a state where the phonons and the Hubbard U cooperate very well, and the Hubbard U helps you to have a distortion, and you go directly into a state where they do not get along very well, and your Hubbard U kills out the phonons. So, and clearly, if you happen to live around here, you will go very rapidly, changing some small material property from one regime to the other. So you may witness the sudden appearance or disappearance of lattice distortions, changing something which from the electronic point of view looks very small. Let me just spend last second to discuss a bit what we have in this intermediate solution. Basically, the intermediate solution is the one where I'm really sitting at the boundary. And here I can obtain a phonon distribution function with 3 peaks. So it's really like my solution has the simultaneous presence of distorted sites in both directions and undistorted sites, which are, if you then examine the wave function, associated exactly to the configurations we've discussed before. So in this case, actually, as you may know, in some cases, when you have a transition between 2 insulators, you may happen to have a metal. This is the case, for example, of the previous result that I've shown for the Hubbard-Holstein model, or something you can find also in, in the Hund's physics system. In this case, it's actually an insulator, but actually it's not that surprising, because you see, if you look at the state where you have these configurations, there is no hopping process that brings you from one to the other. So in the end of the day, these are totally disconnected and you stay into an insulating one. Of course, this only happens on a line, so it's really, really extreme fine tuning. But then if you dope, what used to be a sharp transition becomes now a crossover. These are basically lines for different values of density. And then basically you see that, you see this jump here is my transition, now becomes a crossover. And when you have this crossover, you actually turn out to be, to have a wide region of these, where the phononic distribution function has 3 peaks. You have this coexistence of distorted and undistorted sides. That now becomes quite, say, generic. It's not something that you really need to tune your parameters to obtain the result. Okay, so I guess that's basically what I wanted to tell you. And so let me thank the co-workers. The size is proportional to distance in time. So Alberto Cazzola and Adriana Maricci, who is in the audience, have been the main players in the last results. And then you go to, in the past, fullerides, realistic fullerides models with all these guys that I deeply thank. And of course, I mean, maybe there's no need to read my conclusions that basically tell you that the outcome of the competition between electron-electron and electron-phonon interaction can be tricky, interesting, rich. Small changes can trigger huge differences. Then I think that these results can be a really good somehow compass to get oriented in the world of materials. I don't have examples here, but for example, I mean, there are some chromates where I think it's quite clear that we are seeing this kind of physics. And I hope, and then of course, in the future and the present, I'm actually considering some more realistic modeling of system, richer modeling, and so on. So thank you for your attention.